Welcome back everyone to this fifth part in the multiplayer tutorial series. Since the release of the last episode, a new version of Godot 4.3 has been released with a ton of new features. In this episode, I'll show you how to use the updated TileMap system to build the world for the game. Then we'll take a look at the costs of running a multiplayer server with Firebase and some of the shortcomings, as well as how we can solve these. So let's dive in. When you open a project with an updated Godot version, you'll see a warning message that the project was last opened with an older version of Godot. It is a good idea to keep a backup of your project before proceeding here. However, since we don't use any deprecated features, we should be fine. After clicking on OK, the project should open normally as before. One thing that has changed in this version is the setting for running multiple game instances. When we now want to run multiple instances of our game, or testing out the multiplayer functionality, we have some more options to configure these instances. Under Debug, there's now a Customize Run Instances entry. In the top left, we can enable multiple instances and change the number of instances. We can now simulate up to 20 players simultaneously connected to the server. And as you can see, the game still runs smoothly. Let's move on to the tile map. In the last episode, we already imported the hills and water tiles from our asset pack into the Godot project. If you missed that, there's a link in the description below to the art pack. In the old TileMap system, we would have created a TileMap node. As you can see, this node is now deprecated and should not be used anymore. It will be removed in a future Godot update. If you still have a TileMap using the old system and want to upgrade to 4.3, there's a built-in tool to migrate the old TileMap to the new layering system. To create a TileMap from scratch with the new system, we will use these new TileMap layer nodes. But first, let's create a node 2D as a parent container for all our terrain layers. We can then add two TileMap layers as children to this container, one for the water background and one for the island we will build. Now we need to create the tile sets for these two layers. First go to the water tile layer and on the right side under tile set, create a new tile set. And in the bottom toolbar you should see a tileset tab appear. This is different from the TileMap itself. So the tileset defines how the tiles are taken from the sprite atlas, while in the TileMap we define how these tiles from the tileset are then placed in the world. So first we have to start with the tileset. For the water tiles, we can drag and drop the water sprite sheet into the tiles. And when we do this, a pop-up will appear, asking us if we want to automatically create tiles for the new sprite atlas. Once we confirm, we can see that our sprite atlas is correctly split into the 4 tiles. Now to place these tiles into the world, we have to switch over to the TileMap. Remember, this is the tool that lets us place the tiles in the world. To draw a single tile, we can just click on any of the tiles, select the pencil tool here, and then start painting. If we want to fill a world with a water background, the easiest way is to select the rectangle tool and then draw a big area of water. Now as you can see, all these tiles are using the same sprite. If you want to fill the world randomly, we can select all of them by dragging. Select the bucket fill tool, make sure that contiguous is disabled, and click on the die. Now if you hover over the world and click, you will see that some of the tiles got replaced at random. Let's move on to our island. Click on the island and do the same procedure. We'll create a new tile set. Go to the tile set tab here at the bottom and drag and drop the hills sprite atlas. Again, confirm to automatically create the tiles. And now we could theoretically start drawing with these tiles. However, drawing this manually is quite tedious. Godot has a built-in feature to automatically draw the tileset correctly, but we have to configure it first. Click on the tileset, terrain sets, and add a new element. Make sure the mode is match corners and sides. Open the terrains dropdown and add a new element there as well. I'll call this hills. Now back in the tile set, we can go over to the paint section and select the terrains property to paint. In the terrain set dropdown, select our newly created terrain set 0, and for the terrain, select our hills. Now we need to define how these tile sets are connected. Luckily, in the art pack, there's a reference for this. You have to go through each tile and mask out the parts of the tiles according to the reference. At the end, your tileset should look something like this. Now we can go back to our tile map, click on the eraser to remove the previously drawn tiles, go to terrains, select the hills, and again select the rectangle tool. And now I should be able to freely draw the shape of our island, and the tiles will be automatically selected to match up. Now one thing you will notice is that our player is now behind the terrain. To fix that, we can simply drag our tile map above our player node. Now if we run the game, we can see that it works, however we don't really have any collisions yet. To fix that, we first have to create a physics layer on our tile set. So here on the right side, to make sure you have the island node selected, and in the node inspector on the physics layer, add a new element. Now at the bottom in the tileset tab, make sure that we're in the paint mode and then select our newly created physics layer. Click on this toggle grid snap and select grid snap and select the number of grids to be 3. Now we can define our collision shapes. To do this efficiently, we can create one side and then rotate it, either by clicking on these 3 dots, then click on rotate right, or pressing R. Then we paint, press R again, paint, press R again. And here for the bottom one, I want 2/3 of the tile to be blocked. So I'll adjust the collision and click on the tile to draw the collision. Now to create a corner, we can click anywhere on this line to add a point and then drag them upwards. Add another point like that. And now we have the collision shape for the first corner. Now we can press H or select flip horizontally to create the other corner. Then we can flip vertically and adjust the collision shape for the last 2 corners. One final thing I'll draw are these tiles here, which will just be fully blocking. So we can go again here and reset to the default shape or just press F. Now if you run the game, you should be able to walk around, be constrained by the collisions of the terrain. To add a final touch, we can adjust the collision shape of the player a bit, so we can walk up a bit more. So in the player base scene, we can select the collision shape and adjust it to be around the player's feet. Now the collisions feel a lot more natural. The next issue that we're now having is that our player sprites are not sorted correctly. To fix this, we just have to enable Y sorting on one of the parent nodes shared between the players. So under ordering, enable Y sort. Make sure to also adjust the set index of the tile map to be lower than the player. So I set mine to -1. We also need to enable the Y sort on the sync player's remote, as all the remote players will be spawned under this node. And as you can see, the sorting now works perfectly. Now let's talk about some of the limitations of using Firebase real-time database as our multiplayer synchronization framework. Firstly, there is quite a bit more lag than with other more traditional multiplayer architectures. The Firebase real-time database was not designed for multiplayer games, and therefore we cannot expect the same performance as with a server tailored to multiplayer games. Another important disadvantage of using the Firebase real-time database for a multiplayer game is that we are quite limited for ways to handle server-side processing, such as for example server authoritative movement to prevent cheating. There is a cloud function service from Firebase, which we could use to build some server-side logic. However, this is again not really built for this purpose and can also be costly. Which brings me to one of the biggest drawbacks, the cost of the service. Firebase is not open source, and we cannot self-host the service on our own machines. The free tier sounds quite generous at first glance, with 10 GB per month and 100 connections. The problem is, with the real-time database, we pay per read of the database, or more accurately, for every byte that is downloaded. Even the writes, which are not directly billable, generate costs, because there's some data transferred for the HTTP connection. I ran some experiments with changing player data every frame, so assuming a game is always running with 2 players. Already the amount of data downloaded exploded, with almost 10 megabytes of data billed in a single minute. If you assume that the average player plays the game 4 hours a day, we are already at 65 GB per month for 2 players. Minus the 10 GB free tier, we would pay for 55 GB, so costing us $55 for 2 players. And these numbers are after considering some optimization for the message payload, so each message we're sending is only 15 bytes. There's just so much overhead on each of the Firebase real-time database interactions. One way we can solve these problems is by creating our own simple server backend that matches the REST API of the Firebase service. That way we don't have to change much in the existing code. The easiest and fastest way to create such a server for me was using Python and the library Fast API. I won't go into detail on how the server works here, but it's basically just the 3 endpoints for updating a player, deleting the player, and streaming player events to the game. If that's something you're interested in, let me know in the comments. The source code for the server is also linked in the description below. Now, to use the server, the only thing we need to adjust in Godot is the server URL to localhost and the port we defined. Now, when we run the game, you will notice a lot less delay because the connection is only local. If you want to play with your friends, you would need to either connect to each other using a network tunnel, for example using zero tier, or on the server in the cloud, for example with AWS, Azure, or Google Cloud. There's a lot more we could add and explore with this project. The setup with Firebase can be a viable solution for multiplayer games with low frequency and low volume data synchronization, such as turn-based games for example. For other more fast-paced games, a traditional dedicated server or peer-to-peer approach is more viable. In the future, I want to explore these types of multiplayer architectures more, as well as some promising frameworks such as Nakama. If you have any ideas or suggestions for what type of tutorial you want to see next, let me know in the comments down below. Stay tuned for the next videos and see you next time. Take care.